Welcome back. We will now look at how we can determine the acceleration easily by plotting the operating point of the powertrain in a force-speed diagram with the running resistance curve. We will also see how easy it is to modify the running resistance curve on a flat road to find the running resistance on a gradient. The running resistance curve is a graphical representation of one part of the vehicle model, showing the sum of the aerodynamic resistance plus rolling resistance plus gradient force. Note that there are different versions of the running resistance curve for different road gradients. Here we have assumed plus 5% road gradient. In any given time, the powertrain force can be plotted as a point in the diagram. The point is plotted at the vehicle speed and the traction force the powertrain is producing in that specific situation. The point will move when the vehicle is driving due to changed traction force and changes in the speed of the vehicle. However, in each time instant there is only one fixed point in this diagram, which describes the situation the vehicle experiences in one specific situation. From the difference between the actual traction force and the running resistance at the same speed, the net force can be calculated, and from net force, acceleration can be calculated. We will now show how there is a simple pattern for what acceleration we get in different speeds and for different traction forces. Assume that the vehicle is driving in 130 km per hour. The powertrain can produce different forces. We first assume that it produces 1500 Newton. The acceleration is net force divided by vehicle mass. In this case, the net force is 0, so there is no acceleration. The force is now increased to about 3000 Newton, resulting in a net force of 1500 Newton. The acceleration at this traction force is plus 1 meter per second square. If traction force is set to 0, the net force becomes negative, minus 1500 Newton, leading to minus 1 meter per second square acceleration, so the vehicle is decelerating. If traction force is set to minus 1500 Newton, the net force is minus 3000 and acceleration minus 2. If we repeat the same analysis at another speed, like 25 km per hour, and then let the traction force vary from negative to positive values, we will of course get the same pattern, but with 0 acceleration point at the lower force, since it is exactly on the running resistance curve. Do you see the pattern? 1500 Newton above the running resistance curve, the acceleration becomes 1 meter per second square in all speeds, and 1500 Newton below the acceleration always is minus 1 meter per second square for this vehicle. The general result is that above the running resistance curve, the acceleration increases linearly with the difference between traction force and the running resistance. Below the running resistance curve, it decreases linearly to higher and higher decelerations. That means that we can draw curves for different acceleration levels in the force-speed diagram. Here you can see curves along which the acceleration is constant. They represent different acceleration values from minus 2 to plus 1 meter per second square in steps of 0.5. And the traction force on the running resistance curve corresponds to 0 acceleration. For example, we can show all the operating points for which the acceleration is plus 0.5 meters per second square. This version of the diagram is very useful to answer the same question as our vehicle model can answer. That is, if the vehicle needs a certain acceleration, what force is required at different speeds? To answer that question for all possible road gradients, we need different versions of this diagram, one for each road gradient. However, that is not very complicated if we remember that the additional force required to increase acceleration with 1 meter per second square roughly is equal to the force required for a 10% increase in road gradient. Now we will see in a sequence how the running resistance diagram changes with road gradient. If we start from the running resistance diagram at plus 15% gradient, and then reduce the road gradient in steps of 5% until we have the diagram for minus 15%. We will see the effect of changed road gradient. Did you see the pattern? Each 5% step in gradient moved the running resistance curve as much as the step between two acceleration curves, which differ 0.5 meters per second square in acceleration. And all the acceleration values move in the same way. When we soon repeat the same variation of road gradient as we just showed, look carefully at this operating point of 1000 Newton in the diagram to see how acceleration in that operating point change for each 5% step in the road gradient. The acceleration is -1, -0.5, 0, 0.5, 1, 1.5, and 2 meters per second square. So, to summarize, the result of the analysis of acceleration and road gradient is that it's very easy to find the running resistance curve for any road gradient if we have the curve for a flat road. By just having one curve for the running resistance for flat road, we can easily analyze the force required from the powertrain in all possible driving situations. Why do we not only analyze this with equations? Many persons like me have a better visual memory than equation memory, and it is often easier to reason about what should happen in a certain situation from the diagram. However, when simulating and when we need very accurate values, the mathematical model is better. Click Next to proceed to an exercise.